Okay, we are going to begin. Thank you for coming. My name is Benjamin Aranda. I'm going to be introducing Fabio Gramazio. In the realm of architecture, a few names conjure up genuine breakthrough as Gramazio Kohler. I couldn't be more honored and excited to be making this introduction. I remember the first time I saw their work, their brick walls around 2006, 2007. And there were a few qualities that resonated with me then that still continue, I believe, in their work today. There was a resourcefulness of material and energy. The robots that they used back then were not custom made for those bricklayings. They were repurposed industrial robots from the assembly line. So they were kind of brought out of retirement and given a second chance as a brick mason. I was always touched by that. There was also an expansion of the field into programming and code. And I think finally the issue that struck me the most when I saw the work as a young practitioner was that behind this mastery of technique was genuinely like a very wild experimentation. The layering of light coming through the bricks. This atmosphere is something that's usually not associated with bricks. And I think behind this is this, maybe something we'll talk about today, but this hacker's creed, if you will, that you must be rigorous in technique, but wild in the result. Fabio Gramazio is an architect with multidisciplinary interests, ranging from computational design and robotic fabrication to material innovation. In 2000, he co-founded the architecture practice Gramazio Kohler Architects, where numerous award-winning designs have been realized. Opening the world's first architectural robotic library at the ETH Zurich, Gramazio Kohler's research has been formative in the field of digital architecture, setting precedence and de facto creating a new research field, merging advanced architectural design and additive fabrication processes through the customized use of industrial robots. This research is outlined and theoretically framed in the book, The Robotic Touch, How Robots Changed Architecture. Please help me welcome Fabio Gramazio to our school.
I think I can take this off, right?
Yes.
Good. Is it okay? Fine. Well, thank you, Benjamin, for the nice introduction. It's a pleasure and an honor to lecture here. Actually, for the second time, I've been here 3 or 4 years ago. So I will, of course, repeat certain concepts. This is normal. I will also show certain projects I've already shown. I think most of you were not here, so it's legitimate. But I have added new stuff and have reshuffled. I always reshuffle things. I was discussing before with Lydia. The nice thing in lecturing is that you have material at a certain point, way too much. Then you have to try to make sense out of it, try to squeeze it in 45 minutes or an hour. And if you do this exercise often enough, then you eventually find new relationship between material that you didn't think of, and this brings you forward. Okay, so let's start. The topic we deal with, this hasn't changed since a long time, or let's say evolves slowly, as you will see in the lecture, is what we call digital materiality in architecture. This is a concept, a term that we created at a certain point in order to describe a problem we're having. The problem was very simple: being at home or feeling at home in two domains, really at home. The digital as well as the physical, material, architectural domain, and understanding through experience, through studying at the beginning of the 90s, for example, that these two worlds would not relate in any way, so that they are very distant, that they are competitive, that although in our personal experience, there were many points where they were relating. So the act of designing and the act of programming, I must say that we do not have, Matthias and myself do not have any computational science background at all. So our experience or our skill in programming, that of course has evolved over time, but at the very beginning was just playing with computers mid of the 80s. So playing with computers that did not have a graphic user interface. So you would have to program these toys, not more than that. But it brought us into an understanding first for a language that is not difficult, much easier than French. French you're obliged to learn, and programming, some basic is more fun. And at a certain point, sort of believing or thinking or feeling that it would be or should be a convergence between these two worlds, but at the same time living in a context when we opened up our firm in 2000, where there were, was a big distance, much more than now between those two things. And in order to capture, this concept as a very first project, or one among the first projects in the practice that would really sort of put this inversion we were interested in, going from data to material, after having, converted everything into data, since the beginning of the 90s, the internet and all those things, all exciting things, but sort of contradictory if you would be in the end interested in building space with material. So we decided to do an installation, a project that, now it's almost 20 years old. Looks, probably for you digital natives, this is prehistory. Looks probably it's a bit silly, a bit odd, but for us it was important because it allowed us to frame or name a few things in a very precise ways, and to put something that was in the air onto the table. So M-Table, this project, is nothing more than a table, a piece of furniture that you can design on a mobile phone. And this is a mobile phone. Actually, this is a smartphone, the first smartphone, although it doesn't look like this. It's 2002. So no, classical feature of a smartphone, but it's programmable. This made the difference, because until this phone, a phone was allowing you to make phone calls, maybe play Snake, but that was it. And this one had apps. Of course, they were not called apps. Nokia didn't know what apps would eventually be. What is tragic, because they went out of business because of this, because somebody else came and invented the app, but they had it already. And here I show you what this application that we program and distributed was allowing you to do. I had a 3D viewer, a very, very low res 3D viewer that allow you to, to turn an object, a table in space. And this was in the very beginning, would allow you to set points on a surface, and to, with the pressure of your thumb, to apply force on these points. And the force would, of course, deform the surface, and the deformation of the surface would at a certain point create a hole, just by an intersection between two surfaces. So a set of very primitive operations in a very strange environment. We could have done this on a CAD program on a PC, but we decided for a minimal interface, for a device that was not felt as a computer, as a working tool, but as something else, something completely new. So you would eventually send this to our server. There was no cloud, so you had to send stuff to us, physically. course, through the internet, but not printed out. But eventually you could have printed out this, because this is the beauty of this mechanisms here. This is the parameters, to describe this object, the super complex object. And it's just a few, and they are even human readable. There is authorship, there is dimensions, there is then, of course, the position, XY position of these points and the magnitude applied on them. That's it. And with this information, if you have the algorithm is, the rules of the game, the design, then you can reverse engineer this, very complex mathematical description of a surface, of a NURB surface in this case. And with a next step, that is also just a translation with a post-processor, you would produce machine code that will just, cut this out of a piece of wood, walnut. So expensive, beautiful, heavy timber. And by doing this, you would, add a few legs, and you would end up having these sort of objects here that are, unique pieces. Very elegant, beautiful, but at the same time, questioning themselves because they have holes. And the whole point here was, or is that, these design features are not added by the designer. The designer gives somebody else tools to intervene in the form. So basically, this project is, collapsing together a lot of points that back then, 20 years ago, were in the air, parametric design, configurators, the internet, the relationship between the author, the client eventually, that were, in our eyes, highly important to architecture and were not discussed at all, just ignored. So what did we have back then? We had digital architecture, experimenting with, basically blobs, trying eventually to build them, not even so often. And then you would have everybody else that would just not care about the digital and its potential and its meaning for architecture. So here we closed this link in a very irritating and disturbing way, producing in the end, it was a limited series of 10 tables, of course, very expensive, but there were hundreds of not built tables. And this is a small, cutout of this rest. Here you see, interestingly, that they are some are more elegant, more beautiful. Others are extremely ugly. Probably wouldn't even work. Although we had a nice algorithm implemented that would check, for sanity, structural sanity of the thing. But what is striking for us, and this was also the message or the result for us, is there is, you give the freedom to clients or laymen of touching at the form, what normally is what designers hate to do, but at the same time, because they look all almost similar, if you design on the algorithm, so just one level up on the rules, you keep all the control you always had as an architect. So parametric design doesn't equal with losing control over things, and this was the great fear a lot of architects and people and designer had when confronted to the digital that was entering aggressively their domain of their profession. One side not understanding it fully technically, but also fearing losing control over what we traditionally do. Now the next question that comes out of such experiments is why should we code, or what is coding? And of course, this question has also evolved a lot, because if you code as an architect today, probably you don't write code, but you visually connect things in Grasshopper, for example, but it equals coding. So you describe how data should be processed and what happens. You create structures, hierarchies, and become very powerful doing this. But the question still is fundamental, because I've been asked by, I don't know who was it, Eva probably a week ago. Do you think that architects should learn to code? And I said, of course. Everything else would be strange. And probably they should already enter an architectural school knowing how to code. Because I think understanding how the basic, building blocks of our reality. So everything that is around us is driven by these things. Is fundamentally important. Not just to be an architect, to be a designer, but also the more. Now to break down this question on why and where coding becomes interesting or even mandatory, I would like to show a project, a pretty old project we have done, where on which I will focus on two aspects. So this is a village on a lake in Switzerland, very beautiful, but also very complex, a lot of code. So basically here you cannot do anything. And we've been given the task to insert this object there. It's not small, and it has view on the lake. And I would like to first focus on the mass, so on the plan. How is this designed? You see here, it's a rectangle with two cuts. Now these cuts could be just form. Probably they are not. Normally it's not the case, because this is fundamental. If you start to cut such a thing, then it doesn't work anymore. Or Now, if I give you just two hints, it's very clear where this form comes from. First one is house on the right here. This one. This is actually the client. And the client is building in its own garden. Garden is in front of the house, between the old house and the lake. So very usual situation that you have. So you're, as an architect, you're given a problem to solve. Maybe first you have to help identifying what the problem is, but then you start to iterate and you develop solutions. And of course, one solution is to, cut part of the new house in a way that allows to mediate between the size of the new house and the view still open to the lake from the old house. And this is parametric, because once you have decided for the solution, then you can still play on the angle. Bigger angle, smaller house, more view, smaller angle, bigger house, or bigger, maybe easier to organize house. The second cut is even more straightforward, because it is just a matter of access. You have to access with a car. You don't want the car in front of the house, between house and lake. And you need to, you have a radius that lets you in. So here there is not much. You read, the code. You see what cars, what the radius are needed, and then you make the cut. That's it. And you end up with this. Now, why I'm talking about this banal stuff, just to explain that these things are purely parametric. As designer, we are used to frame them, and sometimes, we even program them. But in a case like this, nobody, not even us, we would write one line of code, although it would be super simple, to describe this problem and to feed this problem to a computer. And why is this? It's because the problem is so simple to iterate that we don't need the computer helping us out. You know, we can do this while eating, while talking, while taking a shower, while, you know, sketching. And it's, you know, we don't need optimization. We can find a good solution. We can sell the good solution to the client with arguments, and that's it. Then we draw it up and build it. Now, this is not always the case. And in order to explain this, I now show another aspect of the house that is the complete opposite. Here you see the floor plan. So it's a box with these two cuts, with a core, with vertical. That's a pretty simple organization. It has 2 stories, a folded roof, cantilevering on 4 sides, sitting on this core, and a window ribbon, glass ribbon, following the roof all along the perimeter. Very simple. The slight small problem is the code doesn't allow any glass in this situation, or just a few window, 1 square meter, you know, vertical. This what was the client was looking for. So we used the trick that we already used a few times, and just you know, cladded the whole house with vertical timber slats that would you know, create the effect of a timber house, closed with no openings at all, but actually be completely open if looked at from the interior. Now, here you see how this at the end ended looking, and you see here on this right image that actually there is something going on with this vertical slats. So they are processed, and in this you know, front view and plan, you see what's going on. So these slats are cut or milled at a certain position height, so they're slimmed out. And additionally, if you look here in the plan, these, you know, cut surfaces can be inclined on right or the left side at you know, whatever degree. If you reason about this, you of course find out that this is sort of an engine, you know, a perception, a viewing engine. It allows you to take a screen that is actually homogeneous, and to start to, you know, carve out you know, portions of it that will, because it slims out, open up the field of view. So you play with the field of view. You play with you know, very usual phenomena in architecture. So privacy, sunshade, where, what do you see, what do you hide, and so on and so forth. But it's not yet defined where and how. It's just a mechanism, just parametric again setup that can be designed with. Now, the small issue compared with the first parametric problem is that here we are talking about only 315 parts, what is ridiculously small as number, but they all relate to each other, and they're all different in height, because it's just not a box, but it's a bit more complex box, and this roof is going up and down, and of course you want, you know, this processing of the parts is not related to an exterior drawing that you regularize, but it depends on the glass on the inside, on the spaces, on the program. And here the only thing that you can do is to code. You know, just to be able to design it, you have to write down rules in a way the computer can interpret these rules and show you in real time or almost real time geometry that you as a designer can evaluate. You know, and being a design by nature iterative process where you never know what you will end up with. The only thing you know is that you have to do something in order to be able to assess it and eventually, change it. So trash it or improve it. Then it's clear that without programming, although we are all very good model builders, we also modeler in Rhino, we could model each one of these. Maybe we can be fast and do it in 5 minutes, but add up 5 minutes by 315 and then multiply this by 300. You find out you will not be able to design the way we are used to design. You would have to impose the system and a different logic, that has nothing to do with the thing that you're looking for. And 315 is a small number. Okay. And the second problem then is, how do you build this? Because if you have 315 parts, assuming that you have produced the data somehow by programming or by spending 3 months iterating, then if you would ask a contractor to produce these parts, he would say, okay, this is custom parts. This will cost a lot of money because I have to do, for each single part, I have to measure them in and whatever. Here's where the machine comes in. We had to find a machine that does exactly this and is controlled by digital data. And this is a machine that is very common, because if you order 315 identical slats of a certain height, they will pass them through this machine, because this machine is doing nothing else, than cutting down the surface. First makes it, planar and giving the right height. And the second thing the machine does, because it's able to tilt this blade. Second thing it does, that it can, incline the surface. It's extremely easy. Now, what is the consequence of this, machine? It's that doing this with the data in it, or processed with data, or not processed, costs exactly the same amount of money. I mean, I'm exaggerating a bit because there is logistics, but conceptually, it's the same thing. If you paint this stuff, then you need the paint. So you need to buy additional material that you put on it. So there is work that you should buy it unpainted, is not there. Here it's the same machine. The only difference is the data that goes along with it. This is the result. It's very, very simple. And basically it's a perception machine. You experience it in moving through these spaces, seeing where it goes up and down. Hey, Branko. Hey, nice to see you. Okay, this was the sort of the introduction, just to clarify where we come from, what interests us, what were the what was the motivation to go where we are now, to start playing around with robots. This is then the next chapter, because this is not very conventional. It's implying a lot of nasty technical stuff that often you wouldn't want to do or to know, but the intrinsic motivation is exactly there. How can we transform architecture by making use of the data that is around us anyway, in the most elegant possible way, by instrumentalizing machine and our ability to describe processes. Okay, now the robot. This is a few years now. I mean, it's about the same time, but in another context. This now is research. This is university, where we start in 2005 by buying this machine. And this machine is an industrial robot. So it's not particularly high tech, even back then. It's a mass-produced tool that has changed actually the way things are being manufactured. Cars, for example, cars we buy now wouldn't be, even thinkable without these machines that starts to, be developed in this industry since the 50s. And at the same time, what made this machine extremely interesting for us, beside of being this champion of automation, is the fact that it's anthropomorphic. It's nothing than an arm. So it's not a specialized machine like a router or a printer, or that has been designed with the specific purpose of a process. This machine is bad, really. So this machine is not good at anything. It's not precise. It's not particularly fast. But it's completely open, and this is what makes it, or made it interesting for us back then, and still makes it interesting. So it comes without a tool. And when you buy it, just you have the arm without the hand. And the hand, you can buy some hands, a gripper, for example, or welding. These things are around, but you don't have to. You can also just build a tool, what in this world here is called end effector, that does a specific thing. This means that the design of the tool, becomes part of the design of the process and becomes part of the design itself. And this is a big difference that, for example, in the project I've shown before, there the tool, the machine is already existing. So you have to adapt your design to the machine. What is not bad or a problem, or let's say it's very important, because if there is not a fit there, it will just not work. But by using this machine, or this way to think about machine, then you suddenly open up a large field of or a large design space that, and this is why we went into this, before was not accessible to us architects. Thinking on how to build something is already difficult. We have imaginated ourselves in the last 50 years from the making of architecture to a large extent. But here, this goes even one step further down the line. Here it's not about just discussing how to do something. It's about inventing or reinventing or redesigning the process together with your design. Okay. This is the machine part. Now, the second part is the human. Normally, if you look at prospects of these companies here, you don't see the man sitting on the machine, because this is very dangerous, and this is an artist image. But we did it, and because this is exactly where our particular interest in the machine lies. So we are not, and this is also very difficult to explain, and the source for a lot of misunderstandings. We are not interested in automation. It's as simple as that. We are interested in these machines and their relationship to us. And I could say humans or designers or architects, doesn't matter so much. But we think that the way this machine become productive to us is if we start to relate to them in a non-competitive way. Because there have been, since the 50s, there have been many ways architects looked at machine. Think of the whole history of Kubernetes, from Cedric Price on one end of the spectrum, Nicolas Negroponte on the other side, doing this thinking of these architecture machines, theorizing that the machine would be interesting when it becomes a partner to the human. So this question of who does what and when can you talk to each other has a long history. And at the same time, we feel that there is one thing that is rarely addressed, and this is the legacy of the industrialization, so of the last 250 years, that has sort of created an instinctive fear of these devices for very simple to understand, rationalized reasons. These machines have been designed to substitute tools. I'm oversimplifying, it's clear, but basically the tools of the craftsmen that were little machines, have been substituted by big machines, have been rationalized, taken apart in 200 sub-processes. This is all known, have been expensive, so capital was needed to finance them and so on, alienation of work, blah, blah, blah. And you end up in a post-industrial era we are now in, still being afraid of machines, still thinking on categories. It's us and the machines, and the machines basically make us, lose our jobs. But to a large extent is still true. But the perspective of these machines, post-industrial machines, is completely different. These machines, again, can become tools, that install a relationship to humans that is much closer, although completely different on a technological level, but much closer than the pre-industrial relationship to tools. Something you own, something something you're proud of, something you maybe develop to some extent. Let's think of the tool, and so on and so forth. And that allows you basically to do whatever you want. So you're not stuck in a production line doing this 40 for the 350,000 time, but you are eventually inventing something each time you touch this machine. And now I'm leaving open a lot of parameters. Will this machine be owned by architects, by craftsmen, by cooperatives, whatever? This I don't know. Okay. Now a very short side, a bit didactic side story that I nevertheless think is important, annotations to understand how we imagine this relationship ideally between humans and the machines to be. So this is a brick wall, a built brick wall. This is a drawn brick wall. Drawing is one possible notation for many things, not only in architecture, but also in architecture. Often it's not the best way to notate something if you want to, for example, to bring something to the building site. Here I immediately understand that it's a brick wall, but probably this notation here is much more effective if I have to talk to a mason. And this is a cultural technological convention, the so-called bond type. There are many of them, more or less exotic, and stretcher is something everybody knows, every architect, but also every mason, and it's common knowledge. And stretcher just describes the rules, so the process of how these bricks are organized and laid in space, so the position, but also the sequence. And this allows to describe the whole thing just with a few additional parameters, like the most important ones are the part to be used, so the brick, and the dimensions of the wall. That's it. Extremely compressed, and there are not many misunderstandings if compared with this one. And it's also not so hard to draw. Okay, now what is the parallel of this tiny compressed notation in the digital, in an algorithmic space? It's just now for those of you that don't write algorithms but program with visual, with Grasshopper, this maybe it's not banal to read, but this is just two nested loops. Loop is the basic, one of the basic control structure in whatever all programming languages you can imagine. And if you nest two, one into each other, then you repeat something for a certain amount of times, an action, and until in the inner loop. Once this is done, the outer loop runs, and this allows you basically to do what the mason does, so to mirror what the mason does, because what the algorithm does is to put the brick next brick next brick until you have reached the length of the wall, and then move up to the next level, move by half a brick, and repeat. And this repeating these two processes brings you, to the finished wall. And this is not very exciting. It gets exciting if you look at this. Now this is the same algorithm, but there has been a small modification down here. It's a rotation. The name of the variable, reveals it. How the rotation is calculated is not important at this point, but it's a rotation. So additional information is added to a brick at each, for each single brick at each rotation iteration of this loop. And these, small addition is an act of design. So you need the human. The human now is on the left. The human is playing around with real bricks in space, wants to understand, can you eventually rotate? What can you do with these things? When do things collide? And then he writes these two very easy lines in the algorithm that is identical to the algorithm we have seen before. But it changes it dramatically, because before it was just the same thing as the stretcher bond, just in another notation. Now it becomes this, because it produces this output, and this is not a stretcher bond anymore. I cannot go to a mason and and tell him stretcher bond then does this. This is data, and it's so small because it's a lot. And for each brick you have a rotation. What is simple, but again, not easy if you have hundreds and thousands and hundred thousands of them. How do you describe it? So it's actually non-feasible anymore for a human, or at least not under efficient conditions, architectural conditions. But now this is the small trick to understand the relationship. The machine is expecting nothing else than this, different numbers, and the machine doesn't care if the numbers are all identical or all different. Does not notice it. This is the strength of the machine. And by directly coupling these two things, we are able, and this is now just one possible variant of this relationship, but it's a strong one. We are able to directly link the human designing something, what means in this case to code to some extent, with the machinic act of constructing something, by leveraging on the fact that the machine doesn't care about what for us looks like complexity, but for the machine this is just simple. For the machine, what is impossible for the machine is to understand what a stretcher bond is. Okay. And this is the output, and this is one of these first moment when we felt that we would need a term to describe what's going on here, and where digital materiality. So just opposing these two, terms that don't relate to each other, or didn't want to relate to each other, or described very different domains. So the digital, the rational, cold, so on and so forth, with the material being sensual, warm, haptic, and so on, collapse into one single thing. And what is also important for us, it's that digital materiality is doesn't have to, but often it's a very central thing, because it's not the digital world as we know it, or the way we knew about these things, already in the 90s was computer graphics. But this is just color on paper. Here this thing interact with light. They are purely, genuinely architectural. Okay, and now I would like to go through very quickly two applications that we have been then able to design with this principle. One is a winery for which we designed the facade. Here you see the design process. So the question is again, how do you produce the data? If you now let's reverse the question. If you have this enormous freedom of being able to place, n bricks freely in space or with a free rotation, then where do you get the information from? And this was how we conceived the design process. So we took this building that was existing and filled it with spheres of 3 dimensions. And then mapped the visual information of these, this content, this virtual content, onto the rotation of the bricks. You could do this with, with an image. Herzog Dömerer has done this all the 90s long, But the problem if you map an image is, if you wrap it around, you don't have any consistency, because it's just graphic work. Here, what we were interested in is that this virtual content stays, it's coherent, because if you look at this sphere from this side or from the other, it's always the same. Once you have the data, you just send it to an industrial robot. This was our first machine. We produced this at university. It was sort of a stunt because there are issues of liability and all those things, but sometimes you just have to do things even if they are not so clean, just because otherwise you would not do them. Here you see, process is super simple. The machine is, placing them in space. It's a 3D printing process at a very, very low resolution. We used to say back then, just as the resolution of architecture, because the brick is an architectural element, and then these parts get placed, once they have been transported, just placed onto the skeleton of the building in a conventional, prefabrication process. Here are a few images. And just to remind, this is a building that is, generated by light. There are no, this building changes all day long because the sun moves and changes with position of the observer, changes with the quality of the light, changes according to, you being inside or outside. Because it's completely different physical phenomena that make it readable to your eye. And the sequential roof is a project that is similar conceptually, although here, these things become structural. It's a 2,300 square meter roof, like a canopy. For actually our institute's building, we were lucky to be able to, we got a new building, and we have been able to, convince the board of the school to, insert a small experiment. This is probably the only drawing that exists of this roof. It's nicely showing that if you, at this scale, take, 50,000 timber elements, 5 by 12 centimeters. I don't know now in inches. It's probably 2 inch by a little less than 4 or 5. Something, I don't know. All of different dimension, and organize them in a proper way. So weave them in a proper way. You get a structure that is astonishing for us. That is, consistent, but still malleable. Still stretchable. It's more like a fabric. That can adapt to special conditions. Like here, this is air ducts. That have just to cut through this thing. What you normally do is to cut out something, from the structure, or have the structure running around such situation. Here you just stretch it up, open it up, and have these things going through. And again, 50,000 elements you have to program if you want to organize them, because before we were talking about 315, now it's 50,000. The only way to do is to start from design rules. And this is now this part of the image. I will say, what are the things that I'm interested in? Which are the parts of the geometry that I want to control? How can I describe them? Can I describe them with lines that I can manipulate? Do I want to describe them numerically? Whatever. And then departing from this information that you input, you start to build your design in the form of a program that then adds structure and eventually, and this is very important in these things, creates input data for structural engineers that can check on each iteration, because the same problem, you would just be moved to the structural engineer, because you cannot tell the structural engineer, I give you 3,000 models, and you model them in your structural engineering software, because it takes images. So you have to connect these softwares in order to have this proof that it's working, or the information there that it's not working and where it's not working immediately. And then, going on to the end, at the end, it's, classical beam information when every screw is introduced. The way this roof is built is pretty simple. It's big trusses made of small parts, 15 meter long, 1 meter width, connected by, almost 1 million nails. Now, the nail, this is a specific story, it's because the nail crossed two layers. So in order to avoid collisions here, you really need, sophisticated algorithms that produce this information for the machine at the very end. To end up with a production process that is eventually as simple as the stacking of the bricks, because the only difference here is that the raw part that is normally 6 meter long or longer, so this flat is processed, cut at length, length and a specific angle, and then laid out by just a big robot on a big table. And the robot has not only the ability to deposit these parts, but also to nail them down. So it turns the end effector and then has this, very common tool on it. It is just a nail gun, and gives it the nail. And all this information has to be produced before, because this machine is not doing anything if you don't tell where to nail. Because all of these geometries are different, or can be different, means also that each nail has a specific, or each connection has a specific number of nails and a specific position for those nails. And then at the end, these elements are craned away from the printing bed, installed. So all the subsystem can be installed, but it's very important here because if they're all different, then it's better if you can do this in the shop, transported to the building site, and then craned into position. And this last step is extremely simple because you cook down 50,000 parts, 1 million nails to 168 big elements that can be very simply placed and fixed with a few screws, and that's it. And all the subsystems are in. So it's really about condensing a large number of pieces with the help of algorithms in the design process and machines in order to simplify this last step that has to happen on site to a maximum. Okay. Now, these were two projects that are not super old. The last one, this one is maybe 5 years old. But I wanted to move one step forward from this and show you two projects that we looked at in the last 2 years that work with augmented reality. At a certain point, we realized that this was more of by chance, because we had people in our group that were looking into these things. We realized that we had technologies that basically in principle do the same as Pokemon Go does, just to project something in your visual space, so in your physical reality, but that with the right tools, with the right sensors and the right camera and the right algorithms, you would eventually be able, by tracking position of real objects in space and by extracting the features, so the edges, be able to build tools that could be run on a screen like here or on goggles, or doesn't matter, this is not so important, but that would allow to guide the human to place parts in space. And this would, this is pretty radical, because now the difference we were discussing before between the human and the machine, where the machine is this tool that doesn't care about where things are in space, that doesn't have to measure, here changes. It just becomes a more complex matrix, because suddenly the human too is able to do the same thing, just by being instructed by technology, by a machine. So eventually we did the first project that was fairly simple as a proof of concept. This is it's a diffuser, an acoustic wall, an acoustic diffuser. We designed a piece, a timber piece. It's one piece that can be rotated in 4 positions. And then we have a system, a diffuser works with depth. So you basically create depth pocket where the reverberation of the sound is just not synchronous anymore. So the sound comes back from 2 different distances depending on the wavelength. This creates this phenomena that is it's pretty important and interesting. And then we add again an algorithm organizing these parts in space, these parts produced. And then this was extremely interesting, an experiment with people, not with our group. This would be being completely biased, but with people that normally do this kind of things, giving them these very simple tools, a camera and the screen, with which they could, start to deal with the data on the left that otherwise would be prohibitively, complex and slow. And we were able to produce this as a proof of concept fairly quickly and in a simple way. And with this proof of concept, we transitioned to a second project that by chance came in at the same time. This is a winery in Greece. And the very interesting thing at this winery in Greece is that, it looks very similar to the winery we already did. It's a skeleton, it's a concrete skeleton. The bricks are fillers. The bricks are screens, where air has to go through, but not direct light. There were even more parallels. The client was also an engineer. here, like the first one, the Gantenbein. So somebody that changes profession and starts to produce, in case of Gantenbein, excellent wine. These guys here are starting, but I think they're ambitious, you know. But the big or small difference is while Gantenbein has been produced in Switzerland by a robot, this has been produced in Greece on site by masons. And you see then, if you look, closely, you see in this design here, we have features. For example, we have mortar. Gantenbein didn't have mortar for a simple reason that a robot is not able to put mortar on a brick. This is extremely complex craft. This is dexterity. This is knowledge. This is, And so we had to simplify, to abstract this process. It was nice. It was like a dry wall, with glue, questionable. And with this process here, by being able to use the mason and his knowledge and craft, we have been able to reintroduce the mortar and even, push it one step further by, starting to modulate the amount of mortar. Here you see the working setup. Of course, it's very experimental. The whole hardware was, just prototypical, but it worked. We were able to, provide the mason with all the information he was missing, sort of to adapt the interface in a way that, it would fit to the technique. They place the mortar, then they place the brick. You will see it here, yes. And then, with a best guess, they place the brick on it. And this is a thing that they always do. Even if they do a straight wall, they put it there. And then, with the hammer, they normally tip. And they're very fast. They know if I tip here, I can move the whole brick, translate it down, and squeeze out more. Now with this visual interface where he sees the difference between where it should be and where it is, and it also gets with these red arrows, a visual feedback when it taps. If it's going into the right direction, are able to connect these things. Now, this, of course, has a lot of implications. Probably we'll discuss at the end. What are we doing here? Are we roboticizing craftsmen, or are we reinventing craftsmen? It's very, very ambiguous, but very interesting. Okay, let's move forward. Now, concluding, I would like to move quickly in another direction. Now we are always talking about building material that exist and that we are used to employ, that have a structural history that can be calculated, that are precise, that can be stacked, and so on. Now, I would like to show a few examples of material self-formation, because this is a sort of a second track that can be addressed in an interesting way with algorithms and machine and feedback systems. What you see here is an old, very, very old project, 2007. This is depositing or printing foam with a robot. Polyurethane foam. Polyurethane foam is a two-component material, as you probably know, where when these two components get mixed in the nozzle at high pressure, they start to react. The chemical reaction is started, and this chemical reaction lets the foam up, so change its volume. and of course turn from liquid to solid while foaming up. This is actually what you see here. It's starting slowly. It takes about 2 minutes. It starts to, emerge. Here. So you see this material has a behavior, has a way it's not just a brick that you have to put somewhere or somewhere else or one on top of each other, but this material, and this is particularly a complex thing because this has, it's not just a way it aggregates, when interacting with others. This we'll see later. This material, transforms itself in time, and not in a 10%, but 90% ratio. Here you see that it's exactly what you have seen in the movie. An extremely complex and interesting and almost impossible to fabricate form that is not directly designed, but is the result of a process. And what we normally consider as being design information, geometry, and this is the only geometry we have here on the left, this grid, that is not a grid, it's a path. You see it on the left bottom side. So I have an entry and exit point, but other than that, it's extremely banal, extremely simple, produces this a complex element. And if you wouldn't have seen the material for the movie I showed you before, and if I wouldn't have told you that this is polyurethane foam, then you could not understand the relationship between these things. This is why, because there is a lot of information that you need to design this that is not included or explicit in there. And this is the speed you move and the sequence. The most important thing is the sequence, and this you see on this second one. This is again input and output. You see here a first pass is done, with this big, sine curves, and then a second pass is done with diagonal lines that go from hole here to the next one, to the next one, to the next one. There is a very simple thing happening. It's banal. The first foam has already foamed up. So this is not a line anymore. This is already three-dimensional structure. And when you move with the second line, with the material over it, then it will flow down, along this profile to the left and the right, and accumulate here, and this part's here. So this is the leftover of what flow down, and this is interesting because it's just a result of a sequence. But this sequence is not random. This sequence is included already in here, just not visible, not explicit. Now, if we go to material systems that are a bit less complex, so we decided to abandon polyurethane foam because it was incredibly complex and also not very unhealthy. So not a good thing to do with students. And we found sand is as interesting as polyurethane foam, but a bit easier to handle and fully reversible. This was the second attractive point to us. And again, with a very simple process controlled by a robotic arm, and in this case, a small sensor that measures a distance. This is a dry dot that you have seen. You are able to create extremely, interesting, fascinating morphologies that are just based on movement, speed, sequence, and in the case of sand, height. Because depending on what height you have the nozzle dispensing the material, you add more kinetic energy to the sand, and eventually it will disperse in different ways. We've done a bunch of these experiments, and then started to, at a certain point think, okay, well, how can we use this? Because sand is nice, but it's completely ephemeral. It's very ephemeral. You cannot build anything out of it. It's probably also the beauty. And we decided to use it for fully recyclable molds. And with students created these boxes in which we printed sand. Then with latex, we sprayed a sort of 1 millimeter coat on it that then allowed to, put concrete on it. And if you would put it gently, we would not move the sand away. And then you would decast and, pull away this latex skin and end up with, extremely interesting architectural pieces, very thin, that created literally no waste beyond this super thin skin of latex, because the sand you can directly re-input in the next one. And this is a principle, that has become very important in our research along the last years, because it's evident that what we have to do in the future is to avoid, first of all, CO2 expensive material or intense material, but in best case, avoid to use things only one time. We need to be able to recycle as much as we can. When we build, possibly use elements that have already been built, but when we design also, have the next iteration already in mind and as part of the design. And this is, of course, a very complex thing. There is a lot of discussion going on worldwide. There are many different approaches. And we decided to attack it, from first of all, from a sort of a bit conceptual edge, which is, it's not yet clear how we could use it, but I think it's very interesting because it shows, in the most possible radical way what we talk about, what the goal is. This is jamming. This diagram are describing the phenomena. Jamming is a process or a jamming transition. If you have solid, rigid parts, bodies that have a specific geometry, and you apply constraints to these elements. This can be boundaries or forces. Then you will reach conditions where the material, the parts jam, meaning that they cannot move, they cannot go anywhere anymore. They stay in place, and the whole thing becomes rigid. But by taking the force or the boundary condition away, you can also liquefy it again. So the jamming condition is interesting because it can go, it can be passed in each direction as many times as you want. This is rare in architecture. You can play around with cornflakes. Simple. This is good to understand that it's very much related to geometry. This wouldn't work with spheres, for example. But the question, there has been a lot of research by Achim Menges, for example, on jamming, but they were always looking at designing the parts, finding the ideal part. We said, no, let's think the other way around. What is the material that we have laying around everywhere? It's this. Can be processed in several ways, but actually it just, it's stones, it's gravel. And although it doesn't have the ideal geometry, it's not like cornflakes that just then jams, on its own. We believe that we could make use of this. And here you see, how we started. It's always very playful. We did this with Skylar Tibbetts and this group at MIT already a few years ago. A workshop where we tried every possible combination. So we knew that the gravel alone would not work, that we would need some additional material that we would add to it. And we just went through, experiments. Then, slowly we got better. We started to be able to add load on it. This was when we started to add just string. low quality string into the material, with a layer principle, by actually only creating internal friction. Because if we would have enough friction to, make sure that the last layer of stones would not fall off the surface, creating a chain reaction. But if it would stay in place, then we would have it jammed. So basically, this at this point then were the ingredients of our game. We have done, a lot of experiments in order to, see if this would possibly work, because we had an invitation for producing an installation for the Chicago Biennale, Architectural Biennale. This was 2015, the first edition, and we wanted to do something with this material, but it was absolutely unclear if this would work in a public space, in a museum, in the US, liability and all this story. So we had to very carefully investigate this. This was the first prototyping of then the final installation that was just built to test its robustness and resilience. And here it's very interesting, because you see how this thing, although it's extremely slim, readapts. It takes a long time until the equilibrium is gone, and it reveals what it actually is. Just piled up material. Actually, it's like the heap. But there is this construction process behind, and there is this string that holds it together. Here you see a movie of the and then the final object, where you see how it was produced. This is recycled string. Again, it's very simple. This string would never work in reality. This would degrade. But this was not the point of this installation. The point was, say, let's take the simplest possible materials, aggregate them in a specific way, and have a very performant. So it has printed in layers. Up until it was 4 meters in height. And this, the patterns were all about distributing the forces in a possibly very even way. Then we demolded it. You see here you have jamming still in place, but it starts to collapse. Now this boundary condition is gone. Folded it there. Now it's a block of material, and now by making by using the design property, because the design it's very simple. It's a column. Where the mass three quarter of the mass is placed as high as possible. And then ends up with the very slim legs, 4 legs. And it's about putting the maximum pressure, because pressure is what it, lets it jam onto this slim legs. Here you see the material quality it has. It's interesting because you could destroy it, just by caressing it. This is strange for architecture, because normally, just by hitting it, it's hard. But if you caress it, it destroys. And then this was the logical consequence of this finissage. I don't know if this in English is the same. At the end of an exhibition, when you make a party in order to maybe sell some art, or let's say thanks to everybody and so on. Here we decided to just run the process in the reverse. So to reconnect the string, and to show how this complete separation between the two ingredients could possibly be.
It's interesting that it's so controlled when you demolish it that way. when you pull out the string,
Yeah.
it's actually an extremely
Yeah, because
slow
it's
control.
because it's like a movie, you know. You let it run the other way. Can you know, as long as the string is attached to the ceiling and not, it can only go.
Go straight up.
Yeah,
And then
it goes down up to a pulley and then. Now the very last project that I want to show, and this is also very new. It's from this year. Deals with earth, with clay. Clay is an extremely interesting material. You see it here. This is, you know, what it is in its raw state, because before being, you know, mixed together and with water. This is already mixed, cut, extruded in a cylinder, cut in sections, sort of, you know, we call them malleable bricks. And with this process, we have already done an installation, probably similar to the Chicago installation, so more of an installation where it was unclear what relation it would eventually develop to architecture by throwing these parts in space. Here you see a diagram of the idea. This is the, you know, the physics behind. This is known, although everybody knows that this is not very accurate. Of course, physically it's accurate, but you cannot really use it because there are, you know, there is wind, there is a lot of other factors making sure that it will not land where this diagram tells you. So the thing that you have to do, and this is a, you know, thing we have nowadays, sensor. You set up a feedback loop where you shoot something, you observe, register, track where it lands, and then depending if it's good or bad, you adjust your remaining parameters. For example, you know, the inclination of the shooting mechanisms and so on. This actually is nothing new. You know, the whole military technology has always worked with feedback processes, being them digital or manual, just observation. You know, is the way something like this always worked. Here you see the sensor in the setup, and here you see the process. It's very straightforward. Just you would assume that this ends up just in a big mess, you know, a big heap of material, but actually it's not. Here you see the information from the scanner, which is processed at each iteration. Here you see the material. Here you see the landing of the material, and here you see, you know, the result. And actually, this is really much under control. If you think of, you know, how one of these objects is just thrown in space and just rotates through space, ending up with this is pretty impressive. And the beautiful thing is that, and this is specific to this project, that this, you know, loss of control when throwing is still readable in the, you know, artifact. Because if I go close here, I can, you know, first of all, the brick being malleable exploits its kinetic energy to find its place automatically. So the fact that I don't have full control on where it lands is mitigated by the fact that it will sort of, you know, close the gap. And if it fails, then the next one will close the gap. So there is also a statistical mechanism at work. But when landing, you know, the deformation will tell from where came and in what sequence. So has it deformed when landing, has been deformed by something else. So these extremely interesting structures that you would not design. It's just to give you an idea of, you know, how do you want to control this and build the most sophisticated, you know, end effector. You will never The only way is to accept the fact that you have no control and then, build up control again on the design side.
Does it have to be a cylinder? Did you mention that?
It's easier to extrude, but no, theoretically, it doesn't matter. Now, this last project, this is a clay called clay Rotunda. It's not, I mean, our part is completed, but it will be it's actually a sound studio, or the outer shell of a sound studio in Bern, Switzerland. And here the task was to build, a clay wall 5 meter high. And we wanted to build it not by drawing, but still with discrete elements, with these malleable soft bricks. And we found out very quickly that on the left you see what you would actually need in order to go up there with this material. And if you calculate the mass there, this was completely out of scale. It would have taken a year to produce this thing. So we decided, okay, we want to go just with one layer, so 15 centimeter up there. What doesn't sound so reasonable unless you work on the design and start to deform, give the structural depth that allows to balance out these things, ending up with this very simple archaic shape with one entrance. That then had to be, in order to, stick to the process that we have developed. We did this with industrial robot. You will see it in a minute. You see it here. So this is the space the robot can access from its position, and this is basically needs to become a building block for this big structure. We need to decompose this. And this introduces, a nice building logic that we'll see how it expresses in this movie. That also sums up a bit the whole process. There now you see here what the machine does. So the machine now, with a great deal of control, can push this soft brick in its final position. Now, what is extremely, or has been very interesting to us, is that this is clay. It's super thin and it's clay, meaning this takes about a month to dry. And during this month, this 5 meter high structure is in movement while building, but also when it's finished. So you don't only have to design its final geometry and make sure that this final geometry will be stiff and stable, but you have to look at all the possible intermediate states it can have. If something deflects, you have to intervene while building and at the end, because this shrinks and creates cracks. And this is a thing that you need to start to accept and incorporate in both of your design. You have to work with this pattern that is, just expressing the way it was built. And then you have, and this is more in general, the beauty of working with such a material that is literally, like the jamming project I've shown. This is fully recyclable. You just grind it down and you can build something new with it. It has no, hydraulic binders or whatever. Just water that evaporates. But you have to entertain it. It's designed for decay. And this decay is just visible very quickly. Because if the humidity changes a bit, then you have cracks. And this is it's about is now it's not so related to digital fabrication, but also to digital fabrication to a certain extent, because in our way to conceive digital fabrication, these materials are part of it. Digital fabrication is not exclusively about high tech. It's not the new world, the technocratic solution to everything, but it's about re-enabling solutions that often were already, there, like the materials or the process or knowledge in the case now of augmented reality, where you start to reframe the relation between humans and machines, not in the paradigm of, the industrial era anymore, but in a new relationship. And these are all things that are not evident if you talk about fabrication. It starts there where people are irritated when you say, I'm not interested in automation. This shows that both on a societal level, as well as on a level of our profession, we have really to do a lot of, I would say, fundamental research, but also a lot of communication and theorization in order to be able to communicate these things. And to avoid ending up with big misunderstandings all the time. That sometimes if you're looking for money can be productive, but for architecture and for, answering the big question on how are we going to build the world from now on, because we have to change fundamentally the way we use materials and processes, and resources and labor and so on, they don't help in any way. Because just having things automated doesn't make architecture better, doesn't make it more interesting, doesn't make it more sustainable, just like this. Okay, I think this was a bit of tour de force, but when I reorganize stuff, something it happens. But thank you for listening. And if you still have energy, maybe you can have.
Yeah, that's great.
Yeah.
Yeah, maybe you want to sit down or you want to stand up, relax. Should we sit? You want to stand?
I'm fine with
Fine standing?
Yes.
Stand, yeah. Like I should stand. Yeah, let's sit down, let's sit down. I think it's absolutely it's a very moving body of work, and it tells a remarkable story. But I was realizing towards the end of the lecture that the arc of the lecture has a similar arc to one of your kinds of projects, where it takes the beginning. There's a kind of an establishment of, let's say, principles. There's a long stretch in the first half hour of your lecture of basically setting up the rules of the game, the material that will be toyed with, and in your last hour, maybe half hour of the lecture, there's a flurry of production and a flurry of effects and possibilities, and suddenly we had jamming, we had all this squishy stuff and projectiles, and I feel like it seems like that's also the lifespan of an individual project itself. That the projects you have to hold out for a period of time in order to really know what's possible, and it might only reveal itself at these kind of critical times. down the road. And I think that patience in each project and in your practice, like it really shows through. And I wanted to ask a specific question about that patience, because it seems like where it got to at the end is being able to control what I could only call like second order or third order effects, right? Like where you're beginning to be in control, not really just of the projectile or where it might land, but you're beginning to be in control of the squishiness of the material. And those third order or second order effects, seem to open up really the design field. If I could, be so bold, they seem to give the discipline a kind of new opportunities. But here's the question, like, are they that difficult to access? Do they require this kind of tooling, if you will, or can the second order effects that are so precious and so, as you say, so important to the important issues that affect our culture at hand, can they be accessed more immediately without the kind of let's say tooling that some of your projects demand? I mean, I find the work so inspiring, but I also want it to be, I wonder how we can all achieve this control of the second and third order effects.
Mm-hmm. I think it's also always a matter of time scales also and roles. At university, our role is to look ahead and be radical. And we have the tools to do this. I mean, the financial means, the machines, also the probably we are backed by the culture of the school being a scientific one. Not talking about the Department of Architecture specifically, but the rest of the school is about engineering, fundamental research and so on. And so for us, it's not so hard to argue why we should do certain things. At the same time, this is, not meaning that or suggesting that in the short term, architecture has to operate this way, because it's just not possible, as you say. And this, everybody being in practice knows. We are in practice too. We do many things that cannot make use of such mechanisms. Probably with us, even less that with you, because we have to be really careful not to, allow anybody else to accuse us of, misusing public funds for private practice. If I start to apply something like this in a too direct way in a project, even if it's clean, I'm exposing myself to big risk. Probably 10 years ago, the sensibility was not so high. As saying, this Gantenbein Winery, we were young and wild and probably a bit naive. We just did it, but I wouldn't do it anymore this way, because things have changed. Mixing up
research and practice,
and this was really mixing up. I mean, not in a bad way, but we're just not caring about things. We're not caring. Just wanted to do it. So we found a way. We found a contractor that would pretend that he was making quality control, but actually we were producing it in university in a setup that was not meant to produce anything that would be real, and so on and so forth. But I think the value of going that far is showing up a path, priority. And this is also thing we do in our practice. Then in the real, there is the real world, and this is also evolving pretty fast. If you go out and attentively look at what industry has and what you could eventually, often it's about looking a bit, farther than the techniques that you are used to apply.
Then you find something that with a little bit of additional work, translational work, maybe convincing somebody, can suddenly be used for manipulating a material in a real, building, an economical building context.
Mm-hmm. Yeah, I think, there was some issue that really, this discussion of how it affects the practice of architecture. There was this moment with the Christus Winery, where, and you posed the question as you were talking, are we roboticizing craftsmen here? Where, the brick is getting laid down approximately, and the craftsman is coming in with the final nudge with the computer vision help. And I think it's worth meditating on that for a second, because the profession, at least here in the United States, has become so tied to issues of liability that it's hard to grant too much, let's say, interpretive freedom to the builder. They're often required to color between the lines. And it seems like what this form of computer vision assistance and the kind of looseness of the construction actually re-enables, let's say, the craftsman and their interpretations, maybe even their agency. With the right code, you could also, you could dial that up or down if you wanted. But would you agree that there's possibilities to, I think back to, let's say, masons of a previous century that were given freedom to interpret how to build things. Do you think that there's a kind of a re-enabling of the agency of the builder with these kind of precision technologies?
The builder depends a bit what the builder is. If the builder is a company that develops project to make money,
sure,
then probably not. But the builder, in terms of the company that owns craft, in order to do, to be the best company in town and have the best jobs and do the coolest projects, in order to be proud of it, then yes, there's the potential to reinstore and enable certain mechanisms that have been just erased through industrial production logics that have not really turned, or let's say construction industry has never been fully industrialized.
No,
but there is a lot of ways of thinking that has reverberated into it in the last 100 years. And this question was not a rhetoric question. When we developed this project, we were debating internally if eventually this could be a risk that we would now just automate humans. Say, okay, it's even better. We get the precision of the machine without having to spend money for the machine, and actually, enacting a new form of Industry 2.0 slavery. But then, and these projects were also tracked and monitored on this from this point of view. We found out, and we observed, we talked to these people, we found out that for them, this additional tool was not at all in conflict with their craft. So they didn't felt constrained, but they felt, empowered and augmented, because suddenly it's like an extension to their tool and to their technique, that allows them to do certain things. And, this is not an industrial process to build such a wall. It's you start on one edge, and you end up, when you leave the place, the building is there, and you say, wow, this is cool. And this happens to, I'm a craftsman myself. This is a cool moment. You don't just come in for 2 hours, add a screw, and then leave again and have no clue what the screw was for and how it looks at the end. And you're in control and let's say, of the whole process. It's yours. And I'm convinced that that such techniques are fundamental to allow craft not only to survive, but to reinvent itself and find a new place. And it's very hard to say what this will be. I mean, we can be more or less speculative about it, but it's clear if craftsman, meaning the human that has control on the fabrication, production, construction of something, first person, not mediated through a big company and 100,000 instruction and plans, and then these things have to be integrated. And I think it also will make craft very attractive again, because craft has always been, craft is not just labor, craft is knowledge. Craft is something you learn from your parents or from a specific structure corporation in your town. We're not able to talk about with others. And these are assets. If we think of this new craftsman as being a digital craftsman, being very a person that can program, that runs machines, that is able to talk to the architect, or maybe it's even a designer to a certain extent. These boundaries are very soft. Can be very blurry. Where does and this is also very interesting for us architects, because to talk then to these people. So as architect, we could speculate, okay, could we be also a sort of digital craftsman? What would this mean? Is designing also sort of a craft? Could we get rid of this rigid division between design and construction? Does it make sense still? Or even if we stay with this distinction, the fact that on the other side there is somebody that actually knows and has a lot of control on the process of building, it makes it much more interesting to interact.
And craft has always been something that has evolved through means of production. So it's not a static. It's not like a historical static method.
And I can learn, because the problem right now is if I have a general contractor, I know I'm not interested to talk to them. I just want to fix my plans in a way they cannot escape. And if they tell me something, I know that it's some stupid try to run me, let me do something that will reduce their costs. It can only be about this. I mean, because things are I've never experienced anything else, and probably it's also legitimate. It's the rules. And if you have worked with a craftsman, they're listening, exposing your ideas to him or her is fundamental, because this allows you to, have a good design at a certain point. Without this, there is no design.
Well, I know that there's probably a lot of questions, or people want to jump in or be part of the conversation. Does anybody have anything they'd like to ask Fabio?
I have dozens of things to ask. But, given where we are in time, first of all, wonderful, just love all the work. But I guess I want to double down on a certain moment that Ben was highlighting, and it's a moment where the projects begin to have effects in excess of predictive control, and there's control through it all. There's even control down to getting the mix of the clay that's going to source with enough redundancy to provide the kind of connectivity and structural stability. So this is not a question about relinquishing control. It's a question about when and where is there now an enjoyment of the effects, the aesthetic effects of the accumulation of material that is no longer predicated on the precision of continuous variation being read from code to model to trial to instantiation. But instead now, and I see this in the foam, I see it in the project itself, I see it in the launching of the clay projectiles. It seems that there's also an enjoyment on your end, or master this, if there is, how you understand it. That those kinds of informal variabilities that have to result from introducing an element of a little bit of chance, material chance, projectile chance, all these other things that are going to transform the overall effects of the projects. And was there a moment in time when that happened, or do you see that as a thing that you guys discussed and talked about, or maybe it's also the linearity of certain aspects of the presentation that seemed positioned at some moment in the work that it kind of arrived, or how do you describe it?
I think it has always been there since the beginning, but it has, expanded and sharpened throughout the years of the work. Our decision to go for bricks in the very beginning, of course, was pragmatic, proof of concept, but we were also fascinated by the fact that bricks are not, stainless steel cubes, milled cubes, or 3D printed, whatever design parts, but are just a thing that has been around thousands of years, that has a sort of internalized intelligence, cultural density, that no bricks are identical, that you have huge tolerance you have to work with, so certain friction. You cannot just, think digital. In digital, there is no tolerance. And this has always fascinated us a lot. Now, when we started to work with processes where, we didn't have to add randomness in order to create the not perfect. This was given by the materials on one side, but then at a certain point, just by the technique, if you throw something through space, you don't need random. You're already.
Yeah, you've entered the random.
Heavy, and it's heavy random, and it's very interesting, and it's and this then brings us to another aspect that is also related to this, longing for something that is not perfect. Probably what disturbs us on the pure digital, it's its perfection. And what fascinates us when it comes into the material realm is that it loses this perfection and adopts, aspects of life and of time, for example. This is a thing that fascinates us a lot, and is also related to this techniques and to the materials. Architecture just, ages, just decays. The world decays, and this is why we have to build it all over again. And this is why we cannot afford doing it the way we've done it the last 100 years, basically. There is a lot of things we have to rethink, but also on a very basic aesthetic level. Designing something, knowing that it will fall apart in a slow process, and this can be enacted by, just maintaining it for a certain extent, but that these traces will add on this, pure image it was at the beginning. Traces that can be, read in the material, like the trajectory of the flight trajectory of the projectile in the wall. These are things that we are extremely interested on.
If I might add,
Sure.
Is a lot of the research engaged in what we would call, I guess, in the building industry itself, post-occupancy data mining? So after these things are built and before you pull the string and take them apart, is there a set of tests that you subject them to so that this knowledge can, I would think after successive generations of students and experiments, they can break out of the realm of a site-specific installation and even begin much more actively to engage building practice, hopefully, or ideally. So
It's a good question.
how rigorously do you ask yourselves to do it?
It's a good question because I've skipped this completely here because it just leads too far. But these projects actually are motivated by science.
Yeah.
And they are financed, because of science. So even though Matthias and myself are no scientists, or we don't, we became a bit scientists, so we know the language, we know the value system. We can play scientists easily. We have PhD students and so on, although we are not, this is just, it's not bad, but we have a working methodology that is very aware of the value of this data. And also the whole, mechanisms wouldn't work if we would not be aware of it. But sometimes we just invert the sequence. For example, the jamming transition project. This was developed out of an idea, out of a workshop week, just to see if there was something. Then the Chicago Biennale, we didn't know anything about it. It was all experimental. To find out if we could, put this in an exhibition, 4 meters. It's 2 tons of material in the US. We did a very simple experiment. We put cucumbers, around it, and we collapsed the whole thing, and then we extracted them, and they were okay. We said, it's okay, because the energy, but then once we have done and demolished the Chicago column, we went back. We set up a proposal. It was easier to write having this proof of concept already done. Sometimes it's the inverse. Sometimes you have to hide it, but in this case it was good. And then we asked for money, the Science Foundation, and we got it. And we had 3 PhDs, 2 in our group and 1 in the other group of granular materials, working for 3 years on the science of it. Modeling these things, building prototypes, measuring them, documenting, producing a lot of data.
Great.
But if you are interested, I can show you these things. It's no problem. But in a lecture, this would have exploded all over the place. And there are very, very interesting things to be discovered. For example, what we discovered with these jammed structures is that they are elastic. If you compress them, at a certain point, material starts to break. But if you stop earlier, they will expand again. It's extremely counterintuitive, because how does this? But we measured it. Yeah.
So I'm interested in a lot, the question of the pseudo randomness of the throwing and the jamming and stacking. It all has, or rather, to me, one aspect of that aesthetic is a kind of material honesty of some kind. Like there's something it's trying to lean into the material being itself somehow, even though it's obviously been asked to do a thing maybe it's not normally doing. And I'm interested, especially with the intervention of the string, because it isn't a material, really. Like the stone and string is not a material on its own, but it actually begins to act as a composite once it has this other behavior. And it's the one of your projects that seems to kind of take some pleasure in the kind of unpredictability of an invented material or a composite material or even a kind of deception. And I wonder if you could talk a little bit about whether these are invested in that kind of like honesty or truthfulness, or in what way you're kind of interested in the maybe made up logics of your material invention coming out as part of the experiment.
It's difficult to say. I don't know if I really got your question, but you know, the composite. This is always sort of a paradox and a conflict, because on one hand you would like to do everything with composites, because and to integrate things into each other and so on, and even more in a context, you know, 3D printing, and you know, that allows for it. That sometimes it's almost, you know, predestinated to lead you in this direction. And at the same time, you know that this is, you know, very problematic, because the more things you glue together and the more integrated systems are, you know, we have a lot of, you know, time to learn about this, that there are different, you know, time scales, and that they need to be basically able to disassemble these parts in a reasonable way into almost pure materials, and that it should not take down the, you know, the structure of a building to fix the ventilation, ideally, you know. It's, you know, makes sense, but you know, once it's integrated to, you know, eventually this is the consequence. And where you know, in this specific case of the string, the fascinosum lies is exactly that it's not glued together. It's creating this interaction, but it's a loose one. It's sort of it's just depending on, you know, where and when, you know, it's a temporary thing, can be a temporary thing.
You know, it kind of looks like, though, it almost looks like the string isn't there.
Yeah.
Right? Like it's almost as if there's a kind of behavior of the stone that becomes expressive as a result.
Yeah, it's interesting because the string, I mean, this is interesting from the science point of view, but also conceptually. At the end, what is the string doing? The string is not really holding this thing together. For this, it would be way too weak, you know, recycle the cheap string. It's only making sure that these parts do not, you know, fall off the structure. Because if one, you know, falls off, then the next one and the next one, and you have the chain reaction and the collapse. Still, as thing, you know, stay there. This is also the beauty, you know, that as I said, we had such experiments. You know, how do you destroy this? What's the easiest way to turn it down? It's by doing this. Because actually it doesn't have, it's not glued, it doesn't have any resistance. It's sort of an equilibrium. It's like a surface, you know, tension, like a liquid, you know, tension with a liquid. It can be, you know, get out of equilibrium very quickly. But it's a good question, you know, how this can be expanded, you know, in other you know, domains. Only equilibrium system are, you know, close to this, where you have gravity making sure that things stay in place.
I'm sitting between Ted and Michael, and my comment or observation, and possibly a question attached to it, is lodged right between their questions. I was surprised by the word honesty in your case, because there's such a high level of deception and perceptual twist that is occurring in the work. But I would stop short of characterizing his mannerism as an aesthetic effect, because it is so rooted in latency. So the word probably, if I said everything that you asked, but instead of honesty, put latency in there, it would be very different, because latency somehow emerges out of the plausible and scientific things that may emerge out of means and methods without having ever been done before. But despite all of that, you see you have way too much fun with aesthetic techniques. So there must be something very perverse in your way of thinking, because you understand the relationship between process and outcome also. And so that you're obviously also pushing those aesthetic effects till they, make it all the way to the edge of the cliff right before they fall. And I guess, I don't know what the question is that I would attach to this, but maybe just be more blunt. Do you love the works of the Mannerists and the Baroque and others who are really working with, let's say, known architectural codes and languages, but radicalizing it, even though they are not using your techniques at all?
That's a very, very good question. I would say it's obvious that we love this, and probably it's just a consequence of the fact that although we ventured very deep into science, we're still architects. Now the question is, what kind of architects? Because we have been educated in ETH, super conservative school. Probably still a lot of our, being architect is influenced heavily by this. I often recognize we are, probably by many people, we are, very Swiss, probably pretty boring as architects. Depends a bit on the, scale you apply. But of course, and I mean, in regard to honesty thing, I wouldn't use this term, but what we are interested in is if there is this, convergence between the idea, the thinking, the process, and the tool. We are not. I'm not happy if it's a fuck up. In terms of it doesn't make any sense. You will also be perverse enough to think this is the point. There, I'm just not happy. I'm not interested. But once the mechanism starts to play, then it's obvious that Matthias and myself are very interested to push it beyond what would just make sense to do with it. This is then an aesthetic exploration. The point is only, in order to be able to explore this design space, you have to do the first step. It doesn't come for free. And this is also there where often, this ambiguous status we have, being architects, being researchers, being, at ETH, being Swiss or whatever, being digital at the same time becomes problematic. Expectation management. People that give you money often are more interested in automation of architecture than in architecture, and at the same time, you have to live with it. You have to produce enough of the right answers to survive.
I think we have one more question here. Yeah.
It's great to see your work again and again and again.
Yeah, you must be bored.
But I kind of begin to look for the kind of subtleties and differences in the kind of how you project it in a different way each time. Since Nader kind of tried to kind of qualify your work in a certain way, I thought I would attempt something similar. And from my perspective, there are some obvious intentional dichotomies in what you're doing. You're interested in imprecision, but you're also interested in imprecision. You're interested in determinacy, but you're also interested in indeterminacy in your work. And all of that reminds me of the professor of furniture design in the 60s, David Pye. I don't know if you've heard of him. He taught at Royal Art College in London. And he wrote a remarkable book in 1968 on the nature and art of workmanship. And he contrasted what he called the workmanship of certainty with the workmanship of risk. And in his time, it was industrial production versus the work of crafts. He was advocating some kind of creative merging of the two. And what you're doing, and Matthias really reminds me of what David Pye was arguing for in the 60s.
There's a kind of reaction to over-industrialized production of stuff. So, so you may want to look at that text. I think it may help explain what you are trying to do, because I'm trying to explain to myself, like, what are you trying to do with this work?
Yeah,
It's,
I have to read this.
you know, it's the kind of same frustration that I kind of sense in your work. Okay, we can do stuff that is incredibly precise and realistic, but it's pointless. So yet there is a beauty in starting with something that is deterministic and precise, and then we get up with something that's the complete opposite and ugly, oftentimes.
Mhm.
So you kind of also challenge these aesthetic conceptions of what is beautiful. Like when that mud wall was produced.
I mean, this was interesting with these foam panels.
Yeah.
Because we had a group of students, about 20, and we were late with the robotic setup, as often happens. Consequence of this has been that the students have spent too much time thinking and designing, drawing lines on the computer. And then at a certain point, after certain time, we allowed them, or we asked them to go onto the machine and to run their code, drawing being the code. And the interesting thing has been that they all were horrified by the output. And the reason was that, they did not expect in any way these things to be the result of all their thoughts and, design efforts. And they didn't even look at the result. So it has been a process when reviewing these things, suddenly, to just ask, hey, look at how beautiful this stuff is, how crazy beautiful it is, Would you design something like this? How would you build it? Would you mill it? No way, full of undercut. It has a quality on its own, although it's alien, But you have to reframe this, used mechanism where you say, okay, I draw this, and now I produce it, and it's still this. There's no surprise. There's always a surprise. Of course, with the foam, it's radical because of the material that expands while curing. It's just, it's a big headache, not just because of the chemicals, but also conceptually.
It's really great work. Enjoyed seeing it.
Well, we have gone over, but I do want to does any students have any questions? Yeah.
I'm just wondering if you would be willing to allow this kind of risk and randomness that we deal with within the material to seep into the large scale form as well. Like how much would you be willing to let go of the control when you produce the overall, not just the detail?
It's a good question. Hard to tell. The overall form is it's a vast territory. I think to a certain extent we're very interested in having certain mechanisms dominating. This is a bit what also this strange table project that starts at the beginning of our career. Normally architects do that at the end. They do furniture for some museums they build, or we decided to do it there as a question, starting the whole process. So we're not stiff on form, but we don't really know what the mechanisms could be, because form and function are so entangled often that there is not much space to have other mechanisms governing it. although what this then is a completely new, stream and planet. If we would, and we are interested in it, but we haven't gone so far yet. The question is, what about big data? What about artificial intelligence? As a design mechanisms. Where suddenly, you really start to delegate control on, basic architectural decision to something that is basically a black box.
Yeah.
It's not optimizing things. It's not an algorithm that you can understand, or it's creating something new. But this is a long discussion. But my short answer could be yes, but I have no clue how. Now.
Great. Well, thank you everybody, and everybody online as well for sticking it out. And this was really informative, pleasurable. It was an honor to talk to you. Thank you very much. Let's have a round for coffee.